Welcome to this lecture on the principle of immunology. Today, we are diving into the components of innate immunity. Imagine your body as a fortress. How does it protect itself from the invisible, microscopic invaders that surround us every single day? By the end of this video, you will not only understand the biological barriers that keep you safe, but you will also be able to mathematically model the microscopic battles happening inside you right now. Let us begin. Now that we know what topic we are covering, let us build an intuition for it. To truly understand innate immunity, imagine you are living inside a massive, beautiful castle that holds all the treasures of the world. Outside this castle, there are millions of tiny invaders constantly trying to break in, steal the treasure, and destroy the walls. To protect the castle, you do not just rely on a highly trained army that takes days to assemble. Instead, you have thick stone walls, moats filled with acid, and vigilant guards patrolling the perimeter day and night. In the human body, this immediate built-in defense system is called innate immunity. It is the very first line of defense that you are born with. Building on that castle analogy, let us look at the formal biological definition. Innate immunity refers to the nonspecific, constitutive defense mechanisms that come into play immediately or within hours of an antigen appearing in the body. Unlike the adaptive immune system, which learns and remembers specific pathogens over time, the innate immune system recognizes broad, conserved patterns on the surface of microbes. Because it doesn't require prior exposure to a pathogen to be active, it is considered the natural immunity we possess from the exact moment of birth. It is a crucial holding force that keeps infections in check. Now that we understand what innate immunity is, let us examine its specific components. The innate immune system consists of three distinct types of barriers. First, we have physical barriers, like the skin and mucous membranes, which act as the stone walls of our castle, completely blocking the entry of microbes. Second, we have chemical barriers, such as stomach acid and antimicrobial enzymes, acting like the acid moats to destroy invaders. Finally, we have cellular defenses, including phagocytic cells like macrophages and neutrophils. These are the vigilant guards that rapidly eliminate any pathogens that manage to breach the outer defenses. Having identified the cellular defenders, we can actually mathematically model how they fight an infection. This formula represents the net rate of change in the bacterial population over time, denoted as dN over dt. It equals R times N minus C times P times N. Let us break down these symbols. The variable R stands for the natural growth rate of the bacteria, and N is the current number of bacteria. So R times N is how fast the bacteria are multiplying. The symbol C represents the clearance efficiency of a single immune cell, and P is the total number of immune cells, like macrophages. Therefore, C times P times N represents how fast the immune cells are eating the bacteria. If the number of phagocytes, P, increases, the subtraction term becomes larger, meaning the bacterial population will decrease much faster. Before we move on, let us see this formula in action with a concrete example. Suppose a patient gets a small cut, introducing 1,000 bacteria into the tissue. The bacteria have a growth rate of 0.5 per hour. The body immediately sends 100 macrophages to the site, each with a clearance efficiency of 0.01. We want to find the initial net rate of change of the bacterial population. We choose our immune clearance formula and substitute the given values. The first term tells us the bacteria are trying to add exactly 500 new cells every hour. However, the second term shows the macrophages are successfully eating a massive 1,000 bacteria every hour. Subtracting these gives a final answer of -500. This negative result physically means the innate immune system is successfully overwhelming the infection, reducing the population by 500 cells every hour. This successful clearance we just calculated leads us to an important question. What happens if the bacteria are more aggressive? Sometimes the bacterial growth rate perfectly matches the immune system's clearance capacity. This creates a critical tipping point where the net rate of change is exactly zero. We call this a biological stalemate. By understanding this balance, we can determine the exact threshold number of immune cells required to halt an infection. If the body recruits fewer cells than this threshold, the bacteria will multiply and cause severe disease. Let us look at the mathematical condition for this stalemate. To find that exact tipping point, we use the threshold formula. The formula states that P equals R divided by C. Here, P is the required threshold number of innate immune cells, such as macrophages, needed at the site of infection. The variable R is the natural growth rate of the bacteria, and C is the clearance efficiency constant of a single immune cell. Conceptually, this beautifully simple relationship tells us that the required number of defenders depends entirely on how fast the bacteria reproduce and how efficiently a single defender can destroy them. If the bacterial growth rate R increases, the required number of immune cells P must also increase to maintain the stalemate. Conversely, if the immune cells become more efficient, meaning C increases, the body needs fewer cells to hold the line. Now that we have our threshold formula, let us apply it to a more aggressive infection. Imagine a new strain of bacteria enters the body with a higher growth rate of 0.8 per hour. The clearance efficiency of the macrophages remains at 0.01. We are asked to find how many macrophages the innate immune system must recruit to exactly halt the bacterial growth. Because we are looking for the exact tipping point, we use our threshold formula. P equals R divided by C. We substitute 0.8 for R and 0.01 for C. Dividing these gives us a final answer of 80. Physically, this means the innate immune system must recruit exactly 80 macrophages to the site of infection to stop the bacteria from multiplying further. Any fewer, and the infection spreads. Now that we have successfully used the threshold formula, let us understand exactly where it comes from. We are setting out to prove how the biological stalemate translates into our simple equation. We start with our original differential equation for immune clearance, where the rate of change equals R times N minus C times P times N. To find the exact tipping point where bacterial growth is perfectly balanced by immune clearance, we must set the net rate of change to 0. This gives us the equation 0 equals R times N minus C times P times N. By setting the left side to 0, we have established the mathematical condition for a stagnant bacterial population. This sets the stage for us to isolate our target variable. Continuing from our stalemate condition, let us perform the final algebraic steps to isolate P. We have 0 equals R times N minus C times P times N. First, we move the clearance term to the other side, giving us C times P times N equals R times N. Notice that the variable representing the bacterial count, N, appears on both sides. Assuming the population is not 0, we can divide the entire equation by N to simplify it. This leaves us with C times P equals R. This intermediate step shows that total clearance capacity equals total bacterial growth rate. Finally, we divide both sides by the clearance efficiency, C, to isolate P. This yields our final proven result. P equals R divided by C. We have mathematically proven the exact number of cells needed to prevent a full-blown infection. Having proven the mathematics behind cellular clearance, let us visually review the entire innate immune system. On screen is a diagram illustrating the three fundamental barriers we discussed. Starting on the far left, you see the physical barrier. Notice the tightly packed layer of epithelial skin cells acting like a brick wall, physically blocking the green rod-shaped bacteria from entering. Moving to the center, we see the chemical barrier. Here, a bacterium is trapped in a blue environment, representing lysozymes and stomach acid, and you can see the pathogen actively dissolving. Finally, on the right, we have the cellular component in action. A large purple macrophage is shown extending its membrane to engulf and eat a bacterium, a process known as phagocytosis. This diagram perfectly captures how these three systems work tirelessly to protect you. We have covered a lot of ground today, so let us summarize the key takeaways. First, remember that innate immunity is your body's rapid response security team, providing immediate, non-specific defense from the moment you are born. Second, this defense relies on a combination of physical barriers to keep invaders out, chemical barriers to create a hostile environment, and cellular defenders to eat any pathogens that slip through. Third, we learned that this biological battle can be modeled mathematically, allowing us to calculate whether the bacteria or the immune system is winning. Finally, by understanding the biological stalemate, we derived the threshold formula. P equals R divided by C, proving exactly how many immune cells are needed to halt an infection. You now have a solid mathematical foundation for understanding how your body protects itself every single second of your life.